Welcome to Easy PTech channel. So in this class, we will see the Hamming code for single error correction. In the last class, we have seen how to detect the error with the help of a parity bit. So with the help of Hamming code, we can do single error correction. We can do single error correction. We can detect the error and also we can correct the error. Whereas with the help of parity code or parity bit, we can only detect the error. We cannot correct the error. So whereas with the help of Hamming code, we can correct the error also. So how we are going to do this error correction? So we are able to do the error correction at the cost of extra k parity bits. We are able to do the correction with the help of k parity bits. Whereas in parity code, we are only adding one parity bit. So whereas in Hamming code, we are adding k parity bits to the m information bits. So the total length of the code word is m plus k. To the m message bits or information bits, we are adding k parity bits. So we are able to do the correction with the help of more number of parity bits. So how we are going to assign these m plus k bit locations? So after adding k parity bits, so we are going to have total m plus k bit location, and these are assigned one, the first bit to the MSB out of the m plus k bits, the first bit to the MSB and the m plus k bit to the LSB to the LSB. For example, if you take a 4-bit code word, 4-bit message M1, M2, M3, M4, we are adding, let us add 3 parity bits we are adding. Those are P1, P2, P3. So total will be 4 plus 3, 7. So out of these 7 bits, first bit to the MSB we are assigning, and the 7th bit we are assigning to the LSB. We are assigning to the LSB. So in this way, we will assign the bit location. In this way, we will assign the bit location. So how many parity bits? So what is the relation that should satisfy, or how many parity bits we should add will be decided by this relation. The relation between the number of parity bits and the message bit is governed by this equation. 2 power k should be greater than or equal to m plus k plus 1, where m is the number of message bits, and k are the number of parity bits. For example, if we take m is equal to 4, that means 4 message bits we have. How many parity bits we should add? So if we take k is equal to 1, for example, whether it is satisfying or not, we'll see. 2 power 1 means 2. So what about m plus k plus 1? M is 4, K is 1 plus 1, so that is 6. So 2 is not greater than 6. So K is not 1. So for example, if we take K is equal to 2, that means 2 power 2. So what is 2 power 2? 4. What about M plus K plus 1? M is 4, K is 2 and plus 1. So 7. Again 4 is not greater than 7. So K is equal to 2 is not also correct. So for example, if we take K is equal to 3. So that means 2 power 3, that is equal to 8. What about m plus k plus 1? m plus k plus 1 is 4 plus 3 plus 1, that means it is 8. So it is greater than or equal to. So this is satisfying this relation. So we have to take, for m is equal to 4, the number of parity bits will be 3. So for m is equal to 4, how many parity bits we have to take? We have to take 3 parity bits. So how many parity bits we have to take is governed by this equation. So it has to satisfy 2 power k should be greater than or equal to m plus k plus 1. So how to place these parity bits? We are having the message bits and we are having the parity bits. So where exactly we have to place this parity bit? So the parity bits are placed in the positions of 2 power. In the powers of 2, that means 2 power 0, 2 power 0 means 1, 2 power 1, 2 power 1 means 2 and 2 square and so on. So the parity bits we have to place in these locations 1 to 4. For example, if you for this example m is equal to 4 and k is equal to 3, that means 3 parity bits p1, p2, p3. So what is the code word length? 4 plus 3 7. So that means we will have 7 positions 1, 2, 3, 4, 5, 6, 7. Right? So in these seven positions, we have to place the parity bits these locations 1, 2, 4. So P1, if we call P1, P2, P3 as the parity bits, so these parity bits we have to place in the powers of 240, 241, 242. That means 1, 2, 4. And the next parity bit we have to place in fourth position. And the message bits we have to arrange them in the remaining position. So M1 will come here, M2 will come here, M3 will come here, M4 will come here. So this is the code word. This is the code word after assigning or adding the parity bits to the message bits. This is the code word after adding the parity bits to the message bits. So we have to place the parity bits in the positions of 2 power 0, 2 power 1, 2 power 2 and so on 2 power 3. Now how to find? So for each parity bit will have either 1 or 0. Each parity bit can take either 1 or 0. So how to calculate the value of parity bit? So there is a specific formula, well defined formula to in order to find the value of parity check bits. So how to find? So for this example, so we are taking m is equal to 4. For this m is equal to 4, we are having k is equal to 3. So we are taking p1, p2, p3. So where we are placing p1, we are placing p1 in the 1 position and p2 in the position 2 and p3 in the position 4. So you write the respective binary equivalent of each position. 1 means, for example, 0, 0, 1. 2 means 0, 1, 0. 4 means 1, double 0. So after writing the corresponding binary equivalents, you see for P1 in the binary, the 1 is placed in the LSB position. LSB position. For P2, it was placed in this middle position, and for P3, 1 is present in the MSP position. It is placed in the MSP position. So for calculating the parity bits, we are having total 7 positions. M is equal to 4 and K is equal to 3. So total locations are the number of positions, are the number of bits in the code word are 7. So we are writing for 1 to 7 the corresponding binary equivalent. For 1 it is 001, for 2 it is 010, for 3 it is 011, for 4 it is 100, for 5 it is 101, for 6 it is 110, for 7 it is 111. So now P1 is having 1 in the LSB position. So in the number of bits locations, so wherever you are having LSP1, so consider those positions for P1. So here it is having 1, here it is having 1, for representation of 3, in representation of 5 it is having 1, and representation of 7 it is having 1. So to calculate P1, we will consider the positions of the locations of 1, 3, 5, 7. Right? Next, P2 in the corresponding representation, it is having 1 in the middle position. So consider those locations where the middle positions are having 1. So if you observe the corresponding representation, so here it is having 1, here it is having 1, so here it is having 1, so here it is having 1. So to calculate the parity bit P2, we'll consider the positions 2, 3, 6, 7. Next, P3. For P3, the corresponding binary representation 100. So in 100, the MSP position is having 1. So for P3, you observe the corresponding binary representation 1 to 7. So it is having in the position are the numbers 4, 5, 6, 7. So in order to calculate P3, we have to consider the positions 4, 5, 6, 7. So these are the positions we have to take, and by doing the modulo 2 sum between these positions, modulo 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 2 sum between these positions, we will calculate the parity bit value. We will calculate the parity bit value. So for P1, for example, if you consider the BCD code means it will have number of bits 4. So to calculate P1, we have to do the XOR of 1357. We are having total 7 positions: 1, 2, 3, 4, 5, 6, 7. So for m is equal to 4, we have a is equal to 3. So parity bits we have to place in positions 2 power 0, 2 power 1 and 2 power 2. So these are the parity bit location, and the remaining positions we have to give for the message. So in order to calculate P1, we should consider the locations 1, 3, 5, 7. In 1, 3, 5, 7, in first position P1 it is having. So to find P1, we have to do the modulo sum between. Next, in third position we are having M1, right? And in next fifth position we are having M2, and in the next seventh position we are having M4. So to find P1, we have to do modulo sum of the message bits M1, M2, M4. Next, for P2, in order to calculate P2, we have to do the modulo sum of 2, 3, 6, 7. So in the second position P2 it is having, we need to calculate P2, and in the third position we are having M1, and next in the sixth position we are having M3, and the seventh position we are having M4. Next, in order to calculate P3, we have to consider the locations 4, 5, 6, 7. 4, 5, 6, 7. So in the fourth position we are having the parity bit 3, P3, and in the remaining locations 5, 6, 7 we have M2, M3, M4. So in order to calculate the parity bit P3, we have to take modulo sum of M2, M3, M4. So first I will represent the BCD code. So these are the BCD code. I am placing the parity bits in the positions bit 1, bit 1 and bit 2 and bit 4, and in the remaining positions 3, 5, 6, 7, I am placing the message bit. So these are the BCD code. For 0 it is 0, 0, 0, 0. For 1 it is 0, 0, 1. So we'll have the BCD code from 0 to 9. So for each BCD code I will calculate the corresponding parity bits P1, P2, P3. So if you consider the message 0, 0, 0, 0. To calculate P1, we have to take modulus to sum of M1, M2, M4. M1 modulo M2, if we take it is 0, again it is 0. So for as all are 0, so parity bit P1 and P2 and P3 all are 0. For the digits 0, the parity bits all are 0. Next, we'll calculate the parity bits for 0, 0, 0, 1. Right? For P1, we need to consider the message bits M1, M2, M4. M1 modulo M2, that means 0 modulo 0, it is 0. Next, we have to consider M4, that means this position. So 0 modulo 1 is 1, so parity bit P1 is 1. Next, for P2, we have to consider the modulo to sum of 1, 3, 4. In 1, we are having 0. In 3, M3, we are having 1. Sorry, this here. So M1 and M3 it is 0, and that we have to do modulo sum with M4, right? So M1 modulo M3 it is 0, and 0 modulo with 1 is 1. So P2 is also 1. Next for P3, I will write here for P3. So M2, you see M2 is 0, 0 modulo M3. M3 means again it is 0, and M4 is 1. So 0 modulo 0 is 0, 0 modulo 1 is 1. So P3 is 1. So for the message bit 1, the parity bits are 1, 1, 1. Next, for the digit 2, 0, 0, 1, 0. So that means M1 is 0, M2 is 0, M3 is 1, M4 is 0. So to calculate P1, we have to do M1 modulo M2. So 0 modulo 0. Next, we have to take modulo with respect to M4. M4 is also 0. So this will be 0. So parity bit P1 is 0. Next for P2 it is, what are the bits? M1 modulo M3. So M1 is 0, M3 is 1. So 0 modulo 1 modulo, what is the next location? M4. M4 is 0. So 0 modulo 1 is 1. 1 modulo 0 is 1. So P2 is 1. Next for P3. For P3 we have to consider the locations M2, M3, M4. M2 means 0 and M3 means it is 1 and M4 it is 0. So 0 modulo 1 is 1. 1 modulo 0 means 1. So P3 is also 1. Right? Next we will calculate for the other bits also in this similar way. So for the next code word, right. Next code word, what are the bits? M1, M2, M3, M4. For the digit 3, we are having 0, 0, 1, 1. So P1 is M1 modulo M1 is 0. So 0 modulo M2 is also 0 modulo. Next it is with respect to M4. M4 is 1. So 0 modulo 0 is 0. 0 modulo 1 is 1. So parity bit is 1. Next for P2, M1 is 0 modulo M3 it is 1 and M4 it is 1. So 0 modulo 1 is 1, 1 modulo 1 is 0. So parity bit P2 is 0. Next P3. P3 is M2 modulo M3 modulo M4. So 0 modulo 1 modulo 1. So 0 modulo 1 is 1, 1 modulo 1 is 0. So parity bit P3 is also 0. So for the message 0011, the parity bits are 100. Next we'll see for the next message 1 double sorry 0100 0100 0100. 0100. So for parity bit P1, so what are the message bits? M1 modulo M2. M1 is 0, M2 is 1, and then M4. M4 is 0. So 0 modulo 1 is 1, 1 modulo 0 is 1. Next for P2, M1 modulo M3. So M1 is 0, M3 is 0, M4 is also 0. So 0 modulo 0 is 0, 0 modulo 0 it is 0. Next P3, M2, M3, M4. M2 is 1, M3 is 0 and M4 is also 0. So 1 modulo 0 is 1, 1 modulo 0 is 1. So the parity bits for the next message is 1, 0, 1. Next, for the next message, that is 0101. 0101. We'll see next message. Next message is 0101. For P1, M1 is 0, M2 it is 1 and M4 it is 1. So 0 modulo 1 is 1, 1 modulo 1 is 0. Next P2 means M1 it is 0, M3 it is 0, M4 it is 1. So 0 modulo 0 is 0, 0 modulo 1 is 1. Next for P3, we are having M2, M2 is 1, M3 is 0, M4 it is 1. So 1 modulo 0 is 1, 1 modulo 1 is 0. So for the next message, the parity bits are 0, 1, 0. Next, for the next message, so in this way we have to calculate the parity bits. Next message is 0110. 011 0. Next message is 0110. So for P1 we have to calculate M1. M1 is 0, M2 it is 1 and M4 it is 0. So 0 modulo 1 is 1, 1 modulo 0 is 1. P2, M1 is 0, and next M3 it is 1, and M4 it is 0. So 0 modulo 1 is 1, 1 modulo 0 is 1, 0 modulo 1 is 1, 1 modulo 0 is 1. Next for P3 is M2 modulo M3 modulo 0. So 1 modulo 1 is 0, 0 modulo 0 is 0. So the parity bits are 1, 1, 0. So in this way we can calculate for the other bits also, for the 7th digit, 8th digit and 9th digit, right? So in this way we have to simply do the modulo sum, and then we have to calculate the parity bit. Now we will see one more thing. So if some code word is transmitted, so this is for example, this code word is transmitted. If there is an error at the receiver, so along with the parity bits, we are sending the code word, we are sending the message, and the receiver is received the code word. How to detect and how to correct the errors? So we will use the same logic, and we'll find the code word. So how to correct the errors? To correct the errors, we have to calculate how many parity bits we are having. Those many check bits we have to calculate. Those many check bits we have to calculate at the receiver side. So the positions are same. For parity bit P1, we have considered 1, 3, 5, 7. So similarly for check bit 1, we have to do the modulo sum of B1, B3, B5, B7. Next, for the check bit C2, for parity bit 2, we have considered the bit positions B2, B3, B6, B7. So similarly, for check bit C2, we have to consider the same locations B2, B3, B6, B7. Next, for parity bit P3, we have considered the bit positions 4, 5, 6, 7. So in order to calculate the check bit C3, we have to consider the same locations B4, B5, B6, B7. Now after calculating these check bits, we have to write these check bits in this way: C3, C2, C1. So whatever check bits we have calculated, those we have to write in this way. So if the corresponding is code word is all zeros, the corresponding code word is all zeros, then there is no error. Else, whatever corresponding equivalent code word is given by this code word, so in that bit positions we will have the error. For example, if C3, C2, C1, if it is giving this code word, that means it is equivalent to 5. So that means in the fifth position we have an error. In the received code word. We have an error. In the received code word, we have an error. We'll see with the help of an example. So for example, this is the transmitted code word sequence. 11001110, and in the received code word, due to error in one position, so this is the received code word. How to find which position it is in error? By using the check bits. So here we know, because here we know the transmitted code word and the received code word. For example, the transmitted code word, what is the transmitted code word? We will write the bit positions 1, 2, 3, 4, 5, 6, 7. So the transmitted code word is 1, 1, 0, 0, 1, 1, 0. And the received code word, because here we can know in which position it is in error: 1, 1, 1 0 1 1 0. In which position it is received in error? In the third bit, except the third bit, remaining bits are as it is. So the third bit, it was transmitted as 0, but it was received as 1. How to use the Hamming code bit location? So what we have said, C1 is calculated 1 3 5 7. We have to take the modulo positions of 1 3. So in one position we are having 1, right, 1, and in the next third position also we are having 1, and next in fifth position also we are having 1, and the seventh position we are having 0. So what is the resultant? 1 modulo 1 is 0, 0 modulo 1 is 1, and 1 modulo 0 is 1. Next, for C2, we have to consider 2, 3, 6, 7. 2, 3, 6, 7. So we have to consider the positions 2, 3, 6, 7. What is the bit in second position? It is 1, and next in 3 it is 1, and next in 6 it is 1, and next in 7 it is 0. Right? 1 modulo 1 is 0, 0 modulo 1 is 1, and 1 modulo 0 it is 1. So C2 is 1. Next, C3. For C3, we have to consider 4, 5, 6, 7. For C3, we have to consider 4, 5, 6, 7 position. So what are the bits we are having in 4, 5, 6, 7? In 4 it is 0, in 5 we are having 1, in 6 we are having 1, in 7 we are having 0. So what is the resultant? 0 modulo 1 is 1, 1 modulo 1 is 0, 0 modulo 0 is 0. Now this we have to arrange in this order C3, C2, C1. So what is the resultant code? 0, 1, 1. What is the corresponding equivalent? 3. So it indicates in the third position of the received code word, the third position of the received code word of the received code word, there is an error in the received code word. There is an error in the received code word. There is an error. So in the third bit there is an error. So we have received as 1. So this we have to change. So the correct code word is 11001110. So this is the transmitted code word. So in this way we can detect the error, and we can also correct the error with the help of the Hamming code. With the help of the Hamming code, we can detect as well as correct the error also. Whereas in parity code, we can only detect the error. We cannot correct the error. So that is the drawback of the parity code. But in Hamming code, we are detecting as well as we are correcting. But we are sending more number of bits. In parity code, we are sending only one bit, but here we are sending more number of bits. So that is the trade-off. So here we are able to correct the error, but at the cost of we are sending more number of bits. So thank you everyone for watching. I request everyone to subscribe EasyBTech channel and share to your friends. Thank you.